Okay, this is our last lecture before the examination. So let me answer the obvious question first. You will be responsible from all the topics that we cover. We will try to cover the continuous time Fourier series as much as we can. But if something is left, then you won't be responsible from those particular things that we didn't cover. But anyway, I believe we will be able to finish this continuous time Fourier series. As a matter of fact, we may even have some idea about the discrete time Fourier series representation as well. So, starting from the beginning until the end of the Fourier series, let's say, you will be responsible in the examination. I will try to communicate about the details of this particular first midterm on the Facebook page. If you have any questions, you may contact me. So, the last thing that we have seen was this property. Actually, we were covering the properties of the continuous time Fourier series. The first property was about the linearity. If you combine two periodic signals with the same fundamental period or corresponding to the same fundamental period, then you can combine or add their Fourier series coefficients, and you can scale them correspondingly. So that's the linearity property. And if you have a time-shifted version of a known periodic continuous time signal, then the corresponding Fourier series coefficients will be scaled by e to the minus jk omega 0 t0. For instance, if k is equal to 0, what does it say? It says that if k is equal to 0, b0 is equal to e to the 0 times a0, and e to the 0 is 1. So, obviously, quite clearly, the DC coefficient doesn't change by shifting. But the first coefficient, b1, will be shifted. And this scale, e to the minus jk omega 0 t0, depends on t0. It depends on the amount of shift as well as what index it corresponds to, what frequency it corresponds to. So this is the shifting property. We will see other properties too. For instance, in most of these properties are theorems, and they have quite nice and quite easy proofs as well. You may forget them, you may not remember them, but it's very easy to derive. The third one is one example to that. If you have a time reversal, which means y of t is equal to x of minus t sort of thing, what happens to the Fourier series coefficients? Do you have any guesses about this? Well, let's write the Fourier series representation of x of t again, and that is summation k from minus infinity to infinity ak e to the jk omega 0 t. Right? This was the representation. Then what would be the Fourier series representation of x of minus t from the same equation? You just replace t by minus t, and you will have k from minus infinity to infinity ak e to the minus jk omega 0 t. Okay, this is what you will have. And in order to properly represent this new expression as a summation of positive exponents, not a negative exponent like this one, e to the minus jk omega 0 t. Let's try to make it e to the j m omega 0 t, for instance. And for that we need to have m is equal to minus k, right? This kind of a substitution. And with that substitution, the summation limits will not change. It will be m from minus infinity to infinity, am e to the, a minus m, because if it is ak, and since m is equal to minus k, k is equal to minus m. So this will be a minus m e to the jm omega 0 t. This m that we have here could be thought as m from infinity down to minus infinity, because it is inverted, but it corresponds to the same running limits anyway. So this is our new representation, which says that the new Fourier series coefficients are these. And what does it say? It says just a negation of the index. So it means if y of t is equal to x of minus t, then the corresponding Fourier series coefficients bk's of this time inverted version of the original signal would correspond to a of minus k. Just an index negation. Because, as you see, we have a minus m here as the Fourier series coefficient. The Fourier series coefficients are flipped around the zero frequency. Do you remember that I was telling you that in cases of real signals, the right-hand side and the left-hand sides have the same magnitude. They are just conjugates of each other. That's what I have told you. For example, a minus 1 is the conjugate of a1. For a cosine omega 0 t, single cosine, what were the Fourier series coefficients? Do you remember? From the Euler's expansion only, without any calculations, what was the expansion of cosine? It was 1 over 2 e to the j omega 0 t plus 1 over 2 e to the minus j omega 0 t. So at k is equal to 1 and at minus 1, the coefficients are 1 over 2 and 1 over 2. 2 1 over 2s. At k is equal to 1 and k is equal to minus 1. If we flip it around, what happens? If we interchange their places, nothing happens. A minus 1 is already equal to a1. They are both 1 over 2. So it doesn't change. And from there I can immediately see that, well, cosine must be a signal which obeys this property. X of minus t is equal to x of t. And if you just visualize cosine in your head, you will see that it is symmetric around the origin. So if you flip it around, it corresponds to the same cosine. And same is valid for the Fourier series coefficients. The Fourier series coefficients are the same too. However, that is not true for sine omega 0 t. Because from the Euler expansion of sine, do you remember what was the Euler expansion of sine? It was 1 over 2j e to the j omega 0 t minus 1 over 2j e to the minus j omega 0 t. Right? So one of the Fourier series coefficients at k is equal to 1 is 1 over 2j. The other one is minus 1 over 2j. Okay? They are conjugates of each other. They have the same magnitude. They are the conjugates of each other. And if you interchange them, you come up with something different. The signs are completely inverted, in other words. So the flipped around version of a sine signal, sinusoidal sine omega 0 t signal, would correspond to minus of itself, because the signs are negated for both of the Fourier series coefficients. So sine of minus omega 0 t is equal to minus sine of omega 0 t. Do you remember what sort of a signal is that? We gave some particular names to such signals. These are exercises. If x of t is equal to minus of, if x of t is equal to x of minus t, we called this an even signal, and cosine is an even signal. And if x of t is equal to negative of minus t, or you can put the minus sign here if you wish, that corresponds to the odd signal. And sine omega 0 t is an odd signal. It is completely antisymmetric around the origin when you flip it around. And you can see the same observation from this particular property as well. Okay. Now the other one. that is time scaling. This is an interesting one, because when you squeeze the whole signal, does anything change in terms of the Fourier series coefficients? Think of a cosine omega 0 t. Okay, signal like that. What were the Fourier series coefficients? It was 1 over 2 and 1 over 2, at minus 1 and 1. If I change omega 0, if I increase or decrease the frequency, if I stretch it or squeeze it, what would be the Fourier series coefficients? It would be again 1 over 2 and 1 over 2. A cosine will always have two Fourier series coefficients of 1 over 2 and 1 over 2, no matter how frequently oscillating, squeezed or expanded version it may be. So in fact, if you have x of alpha t, the Fourier series coefficients of this one will not change. It will again be ak. The Fourier series coefficients don't change by changing or scaling in time. Changing the frequency, it means. Because x of alpha times t will be represented like this. K from minus infinity to infinity. The same ak e to the j k omega 0 times alpha times t. And this alpha can be multiplied by omega 0 only. And it will be k from minus infinity to infinity ak e to the j k alpha times omega 0 times t. I can write it like this. I'm multiplying alpha with omega 0 first. And this will be our new fundamental frequency, omega 0 prime, let's say. But these are the same, the Fourier series coefficients. So what is changing now when you scale in time? It's not the Fourier series coefficients that change. It's only the fundamental frequency that changes. The new fundamental frequency is scaled by alpha, by the amount of scale that you apply to the time in this t. The frequency changes like that. So be careful about that. Don't try to find the Fourier series coefficients of a different cosine or a different rectangular pulse shape that we have seen. The Fourier series coefficients are always going to be 1 over 5, 1 over 3 pi, minus 1 over 3 pi, 1 over 5 pi, minus 1 over 7 pi, and things like that. Again. But the fundamental frequency will be, of course, different. Now, the fifth property. This is quite a fundamental property, and we will be using it in different occasions. Not like this, we will be using it in a different manner, but this is a starting point, and that is called the multiplication versus convolution property. What do we mean by that? Well, this is a general rule of thumb. If you multiply two signals, then the Fourier transform associations will be convolved. And if you multiply the Fourier transforms, that would correspond to the convolution in time domain. The later thing that I told you is not available to us yet. It will be available to us after we cover Fourier transform. For the Fourier series, this is an easier thing. We will multiply in time domain, which will correspond to convolution in Fourier domain. What do we mean by that? It means that if you have a new signal z of t, which is equal to x of t times y of t, multiply them, then the corresponding Fourier series coefficient, let's call it c of k, will be equal to the convolution of AK and BK. So this will be AL BK minus L. The notation may be a little bit awkward because we have seen discrete time convolution with square brackets before. So it's like a square bracket L, b square bracket k minus L. But since we are notating the indices of the Fourier series coefficients as subscripts, that's why I'm putting L and k minus L as a subscript. But can you see that it really corresponds to the convolution of the two discrete time data, AK and BK? They are two discrete time data, like discrete time signals. And you have to just convolve them to find the Fourier series coefficient of the multiplication in time domain, where AK is the Fourier, or AK are the Fourier series coefficients of X, and B are the Fourier series coefficients of Y, of course. You convolve in the other domain. This property in this current form is not very much useful as compared to the Fourier transform that we will see, which says that if you convolve in time, that would correspond to multiplication in frequency in the Fourier domain. And that is an easy way of performing filtering, because we know that by passing through linear and time invariant systems, what we do is we convolve the input X with the impulse response H. So X and H are convolved. Instead of trying to convolve them using that cumbersome operation of convolution, flipping around one of them, sliding, we all remember that. Instead of doing that, just forget about that. Take the Fourier transform of X, take the Fourier transform of H, and multiply them. And then, of course, if you want the time domain signal, you have to take the inverse Fourier transform of the multiplication to come up with the output in time domain. Okay, this is a hint or a glimpse of that property in the opposite direction. So this is discrete convolution. And we will continue with the next property. That is the conjugate symmetry, but I have already mentioned about that. Let's remember what we said. Well, it's actually saying that if you have an even signal, then the Fourier series coefficients will be, in fact, real, like this. Suppose that you have x of t with Fourier series coefficients of AK, then the complex conjugate of it will have Fourier series coefficients of a conjugate of minus k. You can derive this. Just write x of t in terms of its Fourier series representation, the summation, and take the complex conjugate of that whole summation. Why don't we do that? It's a good exercise. Let's write x of t is equal to, so that we can remember better the this representation, because we are going to use it always. It was like this, e to the j k omega 0 t. This was the Fourier series representation as the summation of harmonics with scaled by the Fourier series coefficients. Now let's take the complex conjugate of it. What will be the complex conjugate of the right-hand sided term? It will be a k conjugate. We don't know, it may be complex, therefore that part is also conjugated. And what is the complex conjugate of e to the jk omega 0 t? E to the minus jk omega 0 t. And doing the same trick that we did in order to make the exponent positive, let's make a substitution of m is equal to minus k, sort of thing. And then this will be m from, again, minus infinity to infinity. The order has changed, but it's the same running summation. A minus m conjugate e to the j m omega 0 t. Okay? So what is the Fourier series coefficient here in this new representation? It is here. It's the new Fourier series coefficient, a conjugate of minus m. And this property is telling you at the top exactly that. the new Fourier series coefficients are inverted in order and conjugated. If you conjugate the signal. Now let's start thinking of the cosine omega 0 t. What were the Fourier series coefficients? It was 1 over 2 and 1 over 2, two real things. When we change their orders, make a k as a minus k, and then conjugate them, but they are real anyway, so their conjugates are the same. So if you interchange them and conjugate them, you will get the same thing. Again, 1 over 2 and 1 over 2. Because x and x conjugate are the same. Cosine and its conjugate are the same, because cosine is a real signal anyway, clearly. For the sine, is it the same? Now it's a little bit more complicated, because sine is also a real signal. Therefore, if sine of omega 0 t has ak, then sine conjugate of omega 0 t will still have ak's. Is that true? By making a conjugate of minus k. Let's do it. 1 over 2j minus 1 over 2j. Interchange them. This one will become minus 1 over 2j, and this one will become 1 over 2j. And then negate them. Then conjugate them. And conjugation for j's is just a negation. So minus 1 over 2j will again become 1 over 2j. And 1 over 2j will again become minus 1 over 2j. So nothing will change in the end. It's twice flipping everything. You first flip to opposite sign things, and then negate their signs again, so you come up with the same sequence. And that's why it also obeys this kind of a situation. We can write it, if you wish, for real signals. We have x of t is equal to x conjugate of t. Therefore, a k is equal to a conjugate of minus k. Or, you can write it like this. A minus k is a conjugate of k. So, reversing their orders corresponds to conjugating them. Again, just check it from sign. 1 over 2j and minus 1 over 2j. Flipping around really corresponds to changing their signs, which is plain conjugation. Okay. So this is a property about conjugate symmetry. The conjugation is in the time domain, the symmetry is in the Fourier domain. For real and symmetric signals, if you have a symmetric signal, then it corresponds to an even signal, and even signals have real Fourier series coefficients, and we have a k is equal to a minus k conjugate. But conjugation is unimportant, because for real signals the Fourier series coefficients are, for symmetric signals the Fourier series coefficients are real anyway, like cosine. Cosine was an even signal, so the Fourier series coefficients were real, 1 over 2 and 1 over 2. So there's no need for conjugation. This can be eliminated, and we have a k is equal to a minus k. So for real and symmetric or even signals, we have real and even Fourier series coefficients. These are the best behaving time domain signals that you can think of, because finding a1, a2, a3 is enough to find a minus 1, a minus 2, a minus 3. They are just the same. They are the same from this equation. Alright, and finally, before seeing a few examples, we have the Parseval's theorem. The Parseval's theorem is a power or an energy theorem. depending on the signal, whether it's a power signal or an energy signal. A power signal is usually an infinite extent signal, like a periodic signal. So we have power lines, 50 hertz electricity, for example, and it has a power. Why? Because it's periodic, and it's coming from minus infinity going to plus infinity. For finite duration signals, we have energy concepts. This Parseval's theorem is valid for both power and energy, and it says that whatever power or energy entity you are measuring, you can measure it in time domain, and that would be exactly equal to the measurement of the power or energy in the frequency domain. For the power case, for the Fourier series case, it is like this. The power of a periodic signal is defined as 1 period absolute square integral of our signal. This is the power, normalized by 1 over t. That power is equal to the total power in the frequency domain, which are the square sums of the Fourier series coefficients. That's interesting, isn't it? And that is also quite beneficial. It helps us solve some power calculations in the easier domain, whichever is easier. Is it easier to find that integral? Just integrate there. Is it easier to sum them up in the frequency domain? Just sum them up there. Let's consider the cosine omega 0 t. What is integral from 0 to t in one period? Cosine square omega 0 t, or cosine omega 0 t combined square dt. What is that integral? That corresponds to the power. Of course, you must divide it by t, which is 2 pi over omega 0. What is that? How do you find the... Do you remember how to take the integral of cosine square? Can you do that? Yes, you can do that. Okay, at least theoretically, because in the first year you have seen calculus, so you know how to take the integral of cosine square. But as you see, it's not very easy. I mean, you may remember, but you may as well forget about that. In that case, just why don't you look at the Fourier series coefficient domain, the frequency domain. What were the Fourier series coefficients? We have two Fourier series coefficients. They are both 1 over 2 and 1 over 2. So what is the square of 1 over 2? It's 1 over 4 for this one. It's 1 over 4 for the other one. Sum them. There are only two Fourier series coefficients anyway. 1 over 4 plus 1 over 4 is 1 over 2. So could you guess that that integral corresponds to 1 over 2? Yeah? It's difficult in the time domain. And in the frequency domain, it's almost trivial. The same is valid for sine 2, because everything has a magnitude term. So 1 over 2j's magnitude is 1 over 2, and its square is 1 over 4 again. Another 1 over 4 from the other Fourier series coefficient. Combine them, the total power is 1 over 2 for the sine 2. So that's it. However, of course, for other different signals, for example, the rectangular pulse, what were the Fourier series coefficients? The Fourier series coefficients were 1 over pi, minus 1 over 3 pi, 1 over 5 pi, minus 1 over 7 pi, 1 over 9 pi, etc. Now, what is that series sum? If you take the squares of those terms, 1 over pi squared plus 1 over 9 pi squared plus 1 over 25 pi squared plus 49 pi squared, etc. You go on like that. It's an infinite series sum. What is that infinite series sum? This sign in the frequency domain is difficult to evaluate because there are infinitely many terms. However, in time domain, within a period, it's just a rectangular box, and I am sure you would be able to find the area under a rectangular box. If you take the square of it, it will be again the same rectangular box because the magnitude was 1. So you can just find the area under a box and normalize it by the period. At the left-hand side, this time, in the time domain, it's easier to evaluate. When I first saw this in a book, in a mathematics book, I was in the last year of my high school. I wasn't in the university. I was preparing for the this TÜBİTAK examinations and mathematics with a lot of proofs and things like that. And there was a question of this form: prove that 1 over pi squared plus 1 over 9 pi squared plus 1 over 25 pi squared, etc., plus dot dot dot, which is summation 1 over odd integer times pi's squares, is equal to some value. And it was asking for a proof, and I was shocked and fascinated by the fact that the proof comes from here. It is just the equality of the powers. Of course, I have no idea about what they were talking about then. After the third year, after I covered this signals and systems courses, then I remembered this infinite series summation. Lots of infinite series summations, lots of series summations require the knowledge of Fourier. They require the knowledge of discrete time things like the Z transform that we will see, or the Laplace transform of differential equations that you have already seen. But I didn't know that. And hopefully you will be covering all those things in the third year, including the signals and systems and in control systems or telecommunications of the next semester. By the way, okay, this is the total power, but this thing corresponds to, or it is a specific name, it corresponds to the power of the kth harmonic. Right? Of course, you have to combine all the powers of all the harmonics, available harmonics, to come up with the total power. This is the power of the kth harmonic one. And the Wu meters, equalizers, etc., they are just showing the powers of the kth harmonic. You are increasing that harmonic power by equalizers. Now, by the way, if you want to check the book about this, the properties are total. I'm just giving you some hints about them. They are listed in page 206 of Oppenheim. Just pay attention to those. Now we will proceed with some examples. We will try to solve questions using these properties. Because without these properties, then you will have to solve the questions using those awkward integrals of AK, the formula of AK. And I don't recommend that. Alright. Now what is the question here? Yeah, okay. The question here is this signal. So this is our signal, and the name of this signal is given as g of t on the time axis, and these points are labeled to be equal to, this is 2, this is 4, so you have a 1 here, and this is minus 2, and the values are 1 over 2 and minus 1 over 2. These are the level values. So this is a it looks like a digital pulse or something like that. And the question is, of course, what are the Fourier series coefficients of this thing? And we are going to solve it using the Fourier series coefficients of some other signal that we already know. You can solve it in several ways. You can even solve it using the integration. It's not very difficult, at least. But I'm going to start with something else. And the Fourier series coefficients of this g of t will be notated as decays. Why did the book use decays? Because AK, BK, and CK will correspond to some intermediate Fourier series coefficients of some intermediate signals. The starting signal to achieve this will be x of t, which is the one that we already know. It is this. Where this point is 1, 2, 3, and 4. As you see, both x of t and g of t at the top have the same period. The period is 4, therefore they have the same fundamental frequency. The period for x is 4, the period for g is also 4. And this value is 1, and in terms of x of t we can write g of t. G of t is equal to x of t minus 1. Alright, shifted towards right. And then I subtract a 1 over 2 from that. Can you see that? You just shift this to the right by 1 and then subtract the 1 over 2. So this one level will shrink down to 1 over 2, and the 0 levels will go beyond 0 to minus 1 over 2, which will be precisely g of t. This is the representation of g of t in terms of x of t. Do you agree with that? Okay, if you agree with that, then we can start with the Fourier series coefficients of AK. Which are what? Sine pi k over 2 divided by pi k, except for k is equal to 0, which was something else. But we won't need to consider x of a of 0 when k is equal to 0, because you don't need to evaluate the zeroth Fourier series coefficients of the quotient term. What is d0 of the top figure? What's the DC coefficient? Sorry? No? Look at that. It is positive and negative symmetric. So what is the DC? It is 0. D0, when k is equal to 0, is already 0. So we don't need to consider the zeroth coefficients. Okay, let's forget about it. The zeroth coefficient will be, in the end, it will be equal to 0. We just need to find the others in terms of AK. So if you have AKs, now I will consider only this part and say that, for instance, I will say y of t is equal to x of t minus 1, which will have bk to be equal to. Now what is that? Do you remember the formula? Just please, one of them, you guys tell me what it was. AK times scaled by a complex exponential. What was that? E to the minus, because it's a minus 1 times j times k times omega 0. What is omega 0? Omega 0 has a name. You just don't leave it as omega 0. It was 2 pi over 4. The period is 4, so fundamental frequency is 2 pi over 4. I'm writing 2 pi over 4 here. So AK e to the minus jk, or let's write the e to the term first, e to the minus jk pi over 2 times ak. So these are the Fourier series coefficients of that. Then we are we need to subtract a 1 over 2 from that. So we need to I will do it in a long way, like this. I will call a new signal z of t, which is equal to minus 1 over 2 only, and I will add these two signals later on. But this z of t is equal to minus 1 over 2 has only one term, which is c0 to be equal to minus 1 over 2. And all the other Fourier series coefficients are gone. So if I add y of t and z of t, these two signals, what am I going to do? I'm going to add their Fourier series coefficients. And the Fourier series coefficients of z of t is for only at 0. And these are already found for other case. Well, for k is equal to 0, it was 1 over 2 anyway. So the Fourier series coefficients of these are bk's, and the Fourier series coefficients of these are ck's. You need to add them up. These are 1 over 2, 1 over, well, I need to multiply with the complex exponential. So let's not write them because there are a lot of them. We have already found them here, like this. And we already know ak is to be equal to sine pi k over 2 over pi k. If you wish, we can write it like this. These are e to the minus jk pi over 2 times sine pi k over 2 over pi k. So these are bk's. And ck is only valid at k is equal to 0, which is c0. Let's forget about them because they cancel each other, and we will have the Fourier series coefficient of this one to be equal to dk to be 0 as k is equal to 0. So d0 is equal to 0. And then dk is equal to this thing, e to the minus jk pi over 2 times sine pi k over 2 divided by pi k for k greater than 0. For k different than 0, not necessarily greater. And this is the answer that you have to give me when I ask you the Fourier series coefficients of g of t, the pulse. I asked you this question in an examination some years ago, and many students came up with different answers, and I was very happy with that, because those different answers were mostly correct. If you just expand this sign in Euler's expansion into e to the j omega 0 t and e to the minus j omega 0 t with 1 over 2 j's, okay, just expand them and then multiply with this term. So you will have two different complex exponential terms divided by pi k. Some students came up with that kind of an answer, and I was also happy with that. I mean, they also get full credits. So don't be surprised when you come up with some answers different than what I tell you, because they may be mathematically equivalent to each other. This is a compact way of writing things, but if you expand, you may come up with different compactions. And it's also a nice exercise to try to find the Fourier series coefficients of this g of t using the integral formula. Integration within one period from 0 to 4, for example. In the first half it is once, in the second half it is 1 over 2, sorry. In the second half it is minus 1 over 2. Let's try to solve it. Will you be able to come up with this expression, or at least an equivalent expression to that. It's a lot of algebra. And guess what? I mean, as you may guess, these are the simplest questions that can be thought of, because they are very elementary shapes. For more complicated shapes, we will fall into troubles, which means you will fall into troubles in the examination. The only way to get through those troubles is by exercising. There are many Fourier series coefficient evaluation problems in the book, at the end of the chapter in the book. Please solve them. Just don't say that, okay, the solution is like that and I know it. Solve it with your hands and try not to make any mistakes. Try not to make any errors. That will be a nice skill to develop before the examination. So let's give a break now. After the break, we will continue.